Hi, in this video, we want to take a look at the process of building predictive models. All right, so my goal in this project is to be able to predict the future. I want to basically generate a crystal ball using machine learning. Okay, so when I do this, there's one thing I care about. I care about the accuracy of my predictions. I do not care about how I get it. I do not care about the intermediate steps. I care about the time it takes to do this because I have projects, I have deadlines. But ultimately, I care only about the outcome of my predictions to a major extent. And that's what I want to do. I want to be able to make as accurate of a prediction as possible. Okay, so we're going to go through several steps. First thing I want to emphasize to you is that the earlier the step is, the more important it is. If something goes wrong early on, it's going to propagate all the way through. Now, the flip side of that is that my opinion on learning, machine learning and predictive modeling is that we should learn it in reverse. Okay, so we should learn the in steps first and then go backwards. And so I've been emphasizing like measuring, model quality. Then we talk about modeling. Then we talk about data prep. And this is not the data mining course, so I haven't gone very deep into this. I've just been giving you a flavor of it, giving you appetizers to get you more excited. Okay, so my steps on this is going to be planning. Then we're going to be collecting the data, converting the data to a format that we can use for modeling, explore the data so that we know what we should do to make the data as informative as possible. We're going to prepare the data for modeling. We're going to split the data into train, validation, and test. We're going to build our models. We're going to assess the models. And then we're going to select the best one. We're going to rebuild the best models and with the entire train validation set. We're going to build an ensemble model if we feel like using that, if it's appropriate for our project. And then we actually make our predictions. Now, after step 11, what we'd actually do, we would observe the real outcomes. We would compare the outcomes to our predictions, and then we go through and update our process, look to see what went right, what went wrong. So the key idea is there is one target variable that I want to know about. I want to predict the future on that one target variable. Now, I have corresponding predictor variables, a group of predictor variables that I know what the value is. I want to use these predictor variables to predict this one target variable. Now, I have other data that we call train validation tests. That data I have the prediction and the target variables for that. And we're going to use that train validation test data to actually build the models. All right, so first thing I want to emphasize, the earlier the step is, the more important it is. A mistake, error, poor decision in an early step will propagate all the way through the process. So if there's a problem early on, it's going to be a problem at the end. So we want to be most vigilant on the early steps. Now, if you look at what I've got listed out, those early steps are not sexy. They're not exciting. They're not the steps that you get a lot of emphasis on. You start looking for YouTube videos on machine learning, you do not see a lot about the early steps. It's not exciting to talk about. It's not thrilling. I'm bored of talking about it right now, but it's the most important aspect of it. Now, one thing I think is kind of funny about this is that, in my opinion, the best way to learn machine learning and predictive analytics is to learn it in reverse, like do a reverse learning, a backwards learning. So my opinion is that we should learn to make predictions on a model first. Then we should, okay, I'm going to skip ensemble because that's not going to be applicable for this reverse stuff. We want to learn to build models. We want to learn to assess models, and and then keep on going backwards like that to be able to fully understand what's going on. Why do I view it this way? Well, if I'm learning a step, I really need to truly master and understand that aspect. I need to know the point of it. Why is this important? And so by learning it in reverse, I have a better understanding of that. All right, so this first phase is what I feel is absolutely the most important. And there's very little talk about it when people start talking about machine learning. You'll hear people say garbage in, garbage out. Well, that's usually people like to be like criticizing other people's work, criticize other people's data when you hear them say that. Basically, this step here, steps 1 and 2 are about making sure that you have good data. If I have good data, I can get everything else going. So when I say good data, it means that it is informative for the purpose that I'm working on. All right, so step 1 is basically a game plan. So here, I don't even have data. I'm just making a game plan, and I want to use experimental design. So first, I need to identify the goals of the project, and then I want to identify a feasible target variable that supports the goals. Okay, so what happens in real life is that a decision maker wants this piece of information, but there's no data that directly connects to that piece of information. I go hunting for the data that is most related. Sometimes they're very closely related. Sometimes I'm using a surrogate, and I do the best job I can bridging the gap to make an explanation to show what the best decisions are. Now, this might be for making decisions. This might be for inference. Either way, it doesn't really matter on this step. Now, after I have the target variable that I'm going to be using, I start thinking about the predictor variables that relate to that target variable, that are potentially correlated, potentially connected, potentially correspond to my target data. Now, when I go through this phase, I want to go a little bit, I want to pick up more predictor variables than I really, like if I'm on the fence on whether a variable should be included, I want to include it, assuming that I have the money and time to get it. So we need to talk about the cost and time frame of the project. Now, we want to use experimental design to maximize the informative value of our data. Now, this is something that really is not talked about with machine learning like at all, because why is this? Well, because in reality, steps 1 and 2 are skipped over almost always. What happens is I'm at work, somebody wants information, they come to me, I go to the database, I do a SQL pull, and I run it, and that's it. There's not really a whole lot of thought about information quality in the data. Usually, my experience is that usually it's physicists, psychologists, and statisticians are the ones who really dig into this way of thinking. Engineers also will do this, especially if they're involved in like signal processing, like the people who deal with like signals. Think in the right way for this type of thinking. So experimental design means that I can, so here, if this is for when we're going to be generating the observations, when we're going to be getting the data, some way, some shape, some form, to make it as informative as possible. So remember, on this step, I don't actually have data yet. This is, this is me thinking about how am I going to get data, and how am I going to get that data to be as informative for the project that I'm working on as possible. If the data has not been generated, it has not been collected, you can definitely get more bang for your buck by using experimental design. Right? So think about the situation where, because of cost or time or both, I can only get 8 observations, but yet I'm still expected to make informative decisions or provide a decision maker with information off of 8 observations. That's not very many. It can still be done, but we'll get a lot more out of it if we're mindful of the mathematics behind using data. And that's where this class comes in. All right, the next step is to actually collect the data and just get it. Something to be mindful of is that if there's errors, like somebody records 16 as 61 instead, that's a problem. And that error in that one observation, when they were writing it down, that's going to propagate all the way through my process. If there's noise in my data, so if there's just kind of fluctuations and variations that I can't account for, that makes my data less precise, and those issues are going to propagate through every single step of my project. And most of the time, these two steps are just skipped over. Why are they skipped over? Because usually, people in a lot of organizations, they have data floating around in a database. Someone comes up, hey, I want to know about this. I do a SQL pull, I grab the data, I just run with it. The data is already there. I think about these aspects, but it's very brief. Honestly, as long as you know what data is available and what the question is, usually the person just goes, grabs the data, and runs with it. The next step is to convert raw data into usable data. So imagine a situation where I had data, let's say temperature data for every second of the year, but I need to make predictions on every day. Then I need to somehow convert seconds to days. Or vice versa. Maybe I have data for days, but I need to make predictions by the seconds. I have to be able to convert to a usable format for the problem I'm working on. Our next step is to explore the data. All right, exploring the data, this is where I learn what's truly in there. And this will guide the most important is going to be, or this will have a huge impact on my data prep phase. This is how I know what I need to do when I'm getting the data set right. And if I have data that's coming to me and that's already partitioned, I want to check to make sure that they have the same distributions. So if I have the data I'm using to build the model, the build, validate, and test the model, and I have the data that I'm going to make predictions on, something that I have encountered in real life is that sometimes the data you get to build the model is very different from the data that you need to make predictions on. Okay, think of machine learning algorithms as heat-seeking missiles. It is going to find a data structure with what you give it, and it is going to fit on it, and it's going to fit on it very well. Well, if there's a difference between the data set you're building on and the data you need to predict on, you're going to have problems. All right, so I always check to make sure. Usually how I do this, I use a principal component analysis, and I just check to make sure I color the points by where they're coming from. As long as it looks like they jive, it works out. I've been in the position where the relationship between the predictor variables and the target variables changed between the training and the score data sets. And there's literally nothing I could have done to predict it or anticipate it. I just had to deal with it, had to own up the failure of my models, and it sucked. That was not fun. I mean, I didn't have any repercussions from it, but I wasn't feeling good about my job that day. All right, now, something you want to do on this phase is you want to look for outliers and look for anomalies. I personally try to mute out outliers, and an anomaly is basically the way that I'm using it is it's a value that is atypical with the rest when I look at the collection of predictor variables, but the individual predictor variables don't show it as being an outlier. I would talk about that more if this was a data prep course. All right, now my next step is to prepare the data for modeling. Now here, this is where like all the machine learning books and all of the machine learning YouTube videos start really like digging in because they find it exciting and this is a lot more sexy. But the stuff that came before are the more important steps. All right, so we're going to remove or impute outliers and anomalies if we want to. And okay, everything in this list is basically a choice. Real machine learning, real predictive analytics is really you make choices and you try to make good choices and hopefully you make the best choice. But you will not know if you made the best choices possible until it's too late. So you decide, are you going to remove or impute outliers and anomaly? We can remove redundant or low variable predictors. We want to impute missing values, create missing value patterns if needed. Transform our variables, so if it's numeric, I'll consider the Box-Cox or Yeo-Johnson exponential, log, square root, or discretized transformations, and I misspelled square here. I did this on a different computer when I wrote it up. So you'll notice I'm using the free version of Microsoft Word, so I can't edit it. So just think less of me for misspelling. For ordinal and nominal data, want to consider binning. Consider binning. Oh my gosh. Like when it comes to your categorical data, for the love of God, bin your variables. Bin your predictor variables. I swear it's one of the biggest failures I see in people starting out in this field. Other options we have for categorical data are dummy variables. That's the gold standard in classical statistics, but there's some problems with that. Dummy variables create a lot of predictor variables. The more predictor variables I have, the more prone I am to overfitting. So I don't like dummy variables. I shy away from them if I can, but because they are the gold standard classic way to do it, I get stuck doing it whether I like it or not. Something that mitigates the problems with dummy variables is binning your categorical data together. So you could imagine I have data for every county in the United States. Let's say that. Well, what if I went through and I put them together by geographic region so that I had fewer different distinct levels, that ones that were geographically close were all put into one group? I probably, that might be a better predictor. And if you take data prep with me, I'll talk about like how much binning you should do, when you should not, how you should select groups and whatnot. All right, categorical smoothing. Categorical smoothing is almost never talked about. What it is you replace a categorical, categorical data with the average of the target variable with respect to the level. Let's pretend that I have, let's say, 3 levels, A, B, and C for my categorical data. If I'm doing a regression problem, I can replace A with the average target variable when this one's equal to A. I replace B with the average target variable value when the predictor is equal to B. I'm going to replace C with the average target variable value when the predictor is equal to C. And this is called categorical smoothing. This is not a popular technique. This is one that's frowned upon a lot, but I find that I am less prone to overfitting when I choose to do this. I feel more comfortable with this. I think it is a better choice in most cases. Now for binary variables, consider converting strings to numeric, and consider converting numeric versions to strings. What do I mean by that? Binary is 0 and 1, if it's numeric. Okay, 0 and 1, if I'm looking at that, which one's 0, which one's 1? As I'm working, if I have a lot of variables to work with and it gets confusing, a lot of things are going on, I have to figure out, what does 0 represent, what does 1 represent? So if I had like male, female, male might be 0, female might be 1. Well, if I see 0, 1, like what's 1, what's 0? I have to go and refer back to something. Now, if I have that instead of a 0, 1, I have it as M and F, then it's easier to interpret what's going on, but the numeric version is usually faster for the computer to comprehend or to compute with. So the 0, 1 is better for speed, but like the MF version is better for interpretation, for me understanding what's going on, better for me to make sure that what's going on makes sense. Another thing we can do is center, scale, and range. So center means I subtract off the sample average. Scaling means that we give it standard deviation of 1, and range means I change the range either from like 0 to 1 or -1 to 1 depending on what we're doing. Now, something we'll also want to consider is dimension reduction, such as principal component analysis, ICA, T-distributed stochastic neighbor embedding, non-matrix matrix factorization, pulling out the basis, and there's also spatial sign. My experience is that PCA, TS&E, and the NMF basis are the most useful. NMF basis, non-negative matrix factorization, is most used with text analytics when we're doing bag of words. The T-distributed stochastic neighbor embedding, that takes a long time to compute, so I usually don't use it. PCA is by far the most common. And here we also decided to do feature engineering on this step. Feature engineering is where I take my variables to build new variables. And something I like to do is I use clustering to create a new predictor variable. And so when I do this, remember that if you're doing clustering, the variable is going to be categorical or binary, depending on how you build it up. I personally usually just do 2 clusters. And you'll talk about that in your data mining course. All right, next thing I want to do, I want to split the data into train, validation, test if I'm not doing cross-validation, and train test if I'm doing cross-validation. Okay, so something that the terminology that Python uses like train test, train test, train test. That's all they ever talk about. Okay, training data is the data that I use to build the model. Validation data is the data I use to compare models to evaluate model quality. The test data is my estimate on how well the model will perform in the future. Okay, so Python very much emphasizes train and test and skips over validation. Okay, well, and if I'm doing cross-validation, train and validation are together. They're merged together. So the game plan before computers were really stronger, we would do train validation tests on its own. Like if I have a very large data set or computation time is an issue, I'm not going to do cross-validation. What I'm going to do, I'm going to take a portion of my data. Let's say I'm going to do 50% of my data goes into train, 25% goes into validation, 25% goes into test. Okay, 50% train data, I build all my models on the train data. Now I check to see how does each model perform by making predictions on the validation set. After I do that, the validation statistics tell me which model or models I will keep. I'm not going to use all the models I build. I might build hundreds of models in this process. I'm going to use the validation to pick the model that I want to use. After I'm all said and done, after I'm done building models, I'm going to use the test set as a way to estimate actual model performance. Why do I need this test set? Okay, and this is something I've never really seen articulated well in any book or YouTube video. If I'm selecting the best from the validation sets, you know, if I go through in statistics, I've got a bunch of random variables, and or it may not be random, but we treat it as random. We think of it as random to make it easier to like think about what's going on. All right, my predictor variables are random. My target variables are random. Therefore, my validation statistics, which everything is built off of random variables, the validation statistics are random themselves. Okay, if I pick the biggest or the smallest value, if I pick the best values possible, then that's going to be optimistic. Why? Because I'm picking the best ones. All right, well, if I'm picking the best ones, then things can really only go downhill, you know, down the road. All right, so think about like rookie of the year. The rookie of the year, how well do they do their following year? Well, they do pretty good, but do they do as well as they did during their rookie year? No, they don't. Almost universally, rookie of the year is not as good their second year as they were their rookie year. Why? Because they can only go down. They can only move in the wrong direction because they were at the peak in the first place. So if I'm picking the best models off of validation statistics, I'm expecting the actual performance to be worse. And so I use the test set to give me an honest estimate on how it will perform. Now, if I'm doing cross-validation, what I'm going to do, I'm going to break it up into, let's say, 75% train, 25% test. And cross-validation does the training and the testing at the same time, and the test set tells me what the accuracy will be. Okay, so I'm going to go through. I'm going to build models. I'm going to build multiple model structures for most projects. So I might have a regression. I might have ridge. I might have lasso. I might have support vector machines. I might have random forest. I might have gradient boosting. I might have a decision tree. I will probably have a K nearest neighbor, and I'll probably do a neural network also. And what I'm going to do for each of those model structures, I'm going to work to find the best parameters for each of these model structures. So this can realistically result in hundreds of models. All right, so this can take some computational time also. If I have a large data set, if I don't have much computation power on my machine, this can take a while. Okay, so if I have the whole, if I keep on building model after model after model after model, like the best statistic can only get better on that validation set. But because it can only get better, that means it can only get like more optimistic, which is why I need to do the whole test set thing. All right, so what I'm going to do, I'm going to assess the model performance on the train set and the validation set at this stage. And I can use cross-validation, or I'll do the train validation split. So wherever I get the best validation or cross-validation statistics, that's how I choose my model or models. I always compare my training and validation statistics to look for overfitting. So remember that if the training statistic is worse, and it has to be like kind of a bump. If they're close, it's probably okay. Then I'm going to be looking for outliers to be appearing in my data somewhere. And there, I just have to literally go through and look. Also, as you work through this process, after I get, you have to be ready to always go back to a previous process. Always go back to a previous process. Once I start collecting my data, there really is no going back. Once we get the data going, once we have the data, you can't go that far back. But as you work through the process, you discover, oh wait, I screwed up. I didn't have the raw data processed correctly. All right, I have to go back here and fix it, which means I have to explore the data, prepare the data, split the data, build the model. I have to do that all over again. So a lot of times I'll go through a step, I'll do it, I'm like, oh well, I need to go back, improve what I did. 2 steps, oh well, I need to go back 1, and you keep on doing this, returning back until you feel like you have the best data possible, best models possible, all that. Now, this step is, there's disagreement on this step. This is what I prefer to do. This is most important when you have small data. So I built a whole bunch of models on my training data, just the training data. What some people say you do is you take those models and you run with them, you build them. What I prefer to do, and this also relates to the size of my data sets I work with, is that I take my training, my data, and my validation data, I put them back together, and I rebuild my best models and to get a more representative sample inside the training, inside the data that the model is built on. Some people disagree with this. They have good reasons for disagreeing. This is honestly not that important in a big data problem, but if I only have like 10,000 rows of data, I'm going to strongly consider putting training and validation together and rebuilding. Now, an ensemble model, the game plan here is that I'm going to take the predictions from multiple models and I want to combine them into a better prediction. All right, now the better prediction that hopefully I can improve accuracy, but usually I won't be able to improve accuracy much, but I'll be able to improve the variability. So I'll be able to shave down the error by a little bit. It's not, honestly, it won't be much. If I do everything prior well, the ensemble model isn't going to be a huge improvement. The most I've seen for like a classification problem, the most I've ever seen is like a 10% improvement. So what you want to do here, you take your best models, only your best models, you make predictions with your best models, and then you combine the predictions. So something that is important about this, do not use all your models in this step. Do not use all your model structures, only use the good ones. If you have crappy models and you put them into this ensemble soup, they're gonna make it worse. You only want the good stuff in there. You want a high quality output being thrown into your ensemble models. So the ways that we can do this is that we can take the average. So if I'm doing a regression problem, I can take an average. If I'm doing a classification problem, I can average the probabilities. Now, another way I can do this is that I can take those predictions and I can put them into another model, and this is called stacking. And so I take those, I make all those predictions and then put them into, let's say, a stochastic gradient boosting model, and that gives me my final predictions. I usually use stochastic gradient boosting. I found that's been successful. If you do this, you have to be aware that you know, if you have good predictions, then they're going to be highly correlated, which can cause problems in and of themselves. So you have to be careful about this. This can make you very prone to overfitting. You do this with risk. I go for it, but I'm a wild and crazy guy like that. Now, what we're going to do after we have our predictions, we go through and we actually check how to do our predictions, or sorry, so once I have my models, I'm going to make predictions on the test set, and I'm going to compare the predictions to the actual test set target variable. If I have good predictions there, I'm very confident. If I don't, I need to back up and start at the beginning. This is my honest estimate of how the model will perform. Remember, my train and validation statistics will be optimistic. Also, your out of bag error rate, if you're using a tree model, will also be optimistic also. Honestly, for a lot of problems, I skip over this. Why? Because once I pick that model, I'm running with it. I would rather put that test data, I would rather have a better representative data set by throwing it in. But it's up to you. If you're in a big data situation, I would use a test set, honestly. And then you go and you make predictions on your score data. Remember, your score data is the data you actually want to make a prediction on. Well, that's the steps to it. I know it's kind of vague. It's all just text, but I hope this gives you like an idea of what the true game plan is. And remember, you want to really understand it in reverse. The most important steps are the earlier ones because mistakes early on propagate all the way through. I hope you're having fun. Hope you're enjoying the class. Take care and goodbye.